Hello everyone, this is Xiaolin from Osaka University. Today I will talk about the non-reversible guided metropolis hasting kernel. This is a joint work with my supervisor, Kengo Kamatani. Okay, I will start. As you know, in Bayesian statistics, we always want to sampling from the posterior distribution. And the most popular method is Markov-Chain Monte Carlo, which we also called it MCMC. For most of MCMC algorithm we use, they have the reversible kernel, or maybe you're more familiar with the data balance condition. We like the metropolis hasting kernel here. P is also reversible with its target distribution pi. We concern about the reversibility because it's related to the invariance distribution of the Markov chain, but it's not a necessary condition for the invariance distribution of the Markov chain. Recently, the non-reversible Markov kernel becomes more popular because it has much better convergency property than the reversible kernel. As you all know, there are already some approaches to construct the non-reversible Markov kernel, like modify the accepted rate and flip the moment or HMC, or lifting method in physics. Our proposal is based on the last one, lifting method, and I will tell you the details in the following slides. First, I will give you the definition of delta-unbiased kernel. For summary statistic delta, we call it a Markov kernel. We call it a delta-unbiased if it satisfies the following condition. Basically, you can imagine that in one dimension, it's just like the random walk. The possibility go to left and go to right is same. Now, suppose you already have one delta-unbiased Markov kernel. We see the Markov kernel PG on the product space E and direction space minus and plus is a delta guided metropolis hasting kernel if it satisfies the following equations. It looks a lot equations and very complicated, but the meaning behind it is very simple because the delta guided MH kernel is based on the metropolis hasting kernel. And the only different point is that when the proposal is rejected, the delta guided MH just flip the direction, like here, flip the direction from positive to minus and jump to the other subspace. If you understand this, it's very simple. And because of the delta-unbiased property, the transition kernel and the transition probability Q plus and Q minus is very simple to compute. It's also very easy to check that the invariant distribution of this Markov kernel is pi g, which is the product space. Now the problem is that how can we construct such a delta-unbiased Markov kernel Q? Our proposal is based on a Hara measure, which maps the original state space to a local topology, and which is much easier to construct a delta-unbiased kernel. Here I give the definition of Hara measure nu. So based on the Hara measure nu, we mixture it with the original probability measure mu g, we get a new measure mu star, and with mixture we also get new transition kernel Q star. It's simply just a mixture with the original probability measure and original transition kernel. We found that this new kernel Q star is mu star reversible. So used this mu star reversibility, we propose a new algorithm, which is metropolis hasting with a higher reversible kernel. It's similar to metropolis hasting. The difference is that in each iteration, you first generate a G from a kernel K, and then you mix the K with a transition kernel Q, and then you accept or reject it. At last, it has a invariant distribution. Now, we will give you more strict condition, which is to guarantee that we can construct a delta-unbiased kernel. We call it delta sufficient condition. For a mu invariant kernel Q, if there exists a monokernel Q star, which is equal to Q and only relay on delta x, and also the density of mu with respect to the mu star is only dependent on delta x, then we call this summary statistic delta is delta sufficient. So this is a condition. You may wondering whether this condition is applicable for real case. We will show an example. Now we have a transition kernel Q. Generally, it's a PCN kernel. Then we give a group action GX like this, and higher measure nu based on the mu G and the QG, and the higher measure nu here, like we explained before, we can construct mu star and Q star. Now suppose that we setting a summary statistic delta x like this type, and we get a delta y equal rho product C plus omega. We found that the delta y only depends on delta x because you can calculate this is a general, it's a chi-square distribution, and only depends on delta x. And you also can find that the derivative of d mu and to mu star with respect to mu star is also only depends on delta x. So in this case, the delta is sufficient. Based on this kind of definition and the citing previously, we show our main result. The theorem is that suppose that delta is sufficient for mu reversible kernel Q, and suppose that mu hat and Q hat is continuous. Then Q star is delta unbalanced. So the key point here is that can you find the delta sufficient statistic? If you can find such kind of delta sufficient statistics, then it's very easy to construct a mu reversible kernel. It's very easy to construct a unbalanced delta unbalanced kernel. Based on the theorem previously, we show our proposal algorithm. It's very similar to the previous one, but the difference is that at the first step of each iteration, you decided the direction by summary statistic. If you proposal is rejected, you flip the direction. So the merit is that if you proposal is rejected, you flip the direction and search in new direction. If your proposal is accepted, it encourages you to continue search in such direction. To explain our algorithm, I will show you a toy example. Here is a beta gamma kernel. It's y equal bx plus c and b following beta distribution and C following gamma distribution, and BC are independent. Now suppose we want to sampling from such target distribution, and x1 and x2 are positive. We show you the trace plot of two different algorithms. The first one is simple metropolis. The right one is just a guided version of the metropolis Hastings. It's our proposed algorithm. We can see that compared to the left plot, proposed algorithm can travel much longer, because if the proposal is received, it keeps the direction and travel large steps, so it can explore the target distribution much more efficient. Okay, that's all my presentation, and I think there are a lot of details I haven't explained here. You can find a further reading in the archive paper. Okay, thanks.